For our first video this semester, we're going to talk about solving problems and writing proofs in math. First thing we're going to do is look at what mathematics is and what role proof plays in mathematics. We're going to find a general method about how to prove conditional statements. And then we're going to look at an example theorem, figure out how to prove that theorem informally, and then convert that informal proof into a formal proof. So our first big question, what is mathematics? There are lots of good answers to this question. There's no one specific answer that covers everything. The answer I'm going to give is, well, it's what mathematicians do. And I like this answer for two reasons. First of all, it's a little bit smart alecky, and to be honest, that's a little bit in my nature. But it also gives us some insight into how to approach mathematics. So first of all, it acknowledges that mathematics is what is really defined by a community of mathematicians. We as a community informally decide collectively what is mathematics and what is not mathematics. But even more importantly, it allows us as a class, us as individual mathematicians, to focus on what the actions are of mathematicians to help us become better mathematicians ourselves. So, big question, what do mathematicians do? Well, we do basically four big general things. First of all, we ask a lot of questions about math. And one way of saying that a little bit more precisely is we make up problems to solve. If we don't have problems as mathematicians, we don't have a job to do. Honestly, I don't get paid if I don't have questions and problems that I'm working on. Once we make up the problems, we try to answer those questions. And again, a more precise way of saying that is we solve the problems that we make up. And once we have solved those problems, we have to convince other mathematicians that the solution is correct. If the mathematics only exists in my mind, it doesn't do mathematics any good. It's really important for us to get that information out to other mathematicians. The way we do that is to write formal proofs of those of the solutions of our problems. And then a fourth thing that mathematicians do, we're not going to concentrate a whole lot in our class, is to bring together different parts of mathematics, unify them into a single concept. That process is called abstraction. We'll be doing a little bit of that as a class, but I'm not going to be assigning you that as formal assignments. So we're going to concentrate on writing theorems, those are the statements that we're going to prove, and then proving those theorems. So now we get to the question of what is proof. That's one of the things we're going to focus on in this class. Well, a good description of what a proof is it's a rigorous explanation of why something is true. And what does rigorous mean? Well, that's just a fancy way of saying that there are no holes in your argument. Your logic is airtight. There's no way of being able to say that there's a possibility of your explanation being false. And a good way to sort of think about this, a model that I like to use, is a model I call Peeves. All right? So think of Peeves as someone sort of in the back of your head talking to you, who's trying to make it as difficult as possible for you to prove something. Now, not difficult in a way that they're calling you names or doing like that. They're actually trying to figure out logical holes in your proof. Now, Peeves is definitely bound by the rules of logic. Peeves can't bug you in any way that's not logical, but otherwise, Peeves is welcome to be as disruptive as possible. So, from a computer science point of view, you can think of Peeves as the person who's looking for bugs in your proof. So now let's go to the main type of statements that we're going to be proving this semester. We are going to be proving conditional statements. So, conditional statement is a statement that looks like if P then Q, where P and Q are statements, right? So these are statements that you're probably very familiar with, especially with your experience in computer science, doing programming. You do a lot of if-then constructions. Now, as we learned back in Math 225, the statement if P then Q is false precisely when P is true and Q is false. And it is true in all other situations. And that's really nice in terms of figuring out a way of proving an if P then Q statement, because when P is false, our statement is automatically true, which means that once if I happen to know that P is false, I don't have anything else to prove. The statement is automatically true, which actually means we can ignore this case, right? Because once we've said, well, what happens if P is false? Well, the statement is automatically true. Let's go on to the other possibilities. Well, there's only one other possibility that we have, and that is that P is true, which means that when we are proving an if-then statement, we can assume that the if part, P, is true. Now, once we're assuming that P is true, our statement is false when Q is false, which means that our statement is true when Q is true. So we can summarize this analysis by saying if we want to prove a conditional statement, first of all, we can assume P is true, because when P is false, our statement is automatically true. And then we have to show that Q is true, because if Q is true, then the statement is true. If Q is false, the statement is false. All right, so now we're going to apply this to a particular theorem, but we can't really prove any theorems unless we have something to prove theorems about. So we're going to start with some definitions to get us started. We're going to look at integers, numbers. So an integer is even if it is 2 times another integer. And a more useful way of saying that is a number n is even when n equals 2k, where k is some integer. And an integer is odd if it comes right after an even number. And again, a more useful way of saying that in terms of using it in proofs is a number n is odd when n equals 2k plus 1 for some integer k. In order to get from an even number 2k to the next number, you add 1, and so n equals 2k plus 1 gives us an odd integer. Now that's not the only way we can define an odd integer, but it's the definition we're going to be using for the purpose of this class. So, question, what can you say about numbers that come right after odd numbers? We know odd numbers come right after even numbers. What are the numbers that come after odd numbers? Well, it doesn't take a lot of imagination to figure out what that is. You can probably look at a lot of examples. You could probably use some of your intuition that you've developed over time with numbers. And it is almost certainly true that if n is an odd integer, then n plus 1 is an even integer. So right now, for us, this is a conjecture. Right? But I'm going to write it as a theorem because I'm feeling pretty confident that that is going to be true, but we still have to prove it. All right, so before writing our proof, let's see if we can organize our logic so we can write a nice, clean, elegant proof. So we're going to work out informally why it's true. Now, this is an if-then statement, right? So we're going to assume the if part. In other words, we're going to assume n is an odd number, and we're going to show the then part. We're going to show that n plus 1 is an even number. All right, so let's start with n being odd. What does it mean for n to be odd? Well, the definition of odd number is that n equals 2k plus 1, where k is some integer. Now, that is what we know about n. That's what we're assuming about n. For the purposes of this proof, we want to show that n plus 1 is an even number. Let's see if we can figure out what's going on with n plus 1. Well, what we want to end up with is n plus 1 equals 2 times something, where that something is an integer. It could be any integer. It doesn't have to be k. Right? Anything that's an integer, it could be 2 times 5. That's a perfectly nice one. That's not what it's going to be, but it doesn't have to be k. So let's look at n plus 1. Well, we know what n is. N is equal to 2k plus 1. So let's plug that in for n and see if that gets us anywhere. Right? So n plus 1 equals 2k plus 1 plus 1 because n equals 2k plus 1. And we can simplify this a little bit. The plus 1 becomes plus 2, so we get 2k plus 2. And now we're noticing that, well, each of those terms, the 2k and the 2, have a factor of 2 in them. That's going to be useful because we want to show that this is an even number. So let's see what happens when we factor out that 2. We get 2 times the quantity k plus 1. That's looking a lot like an integer, like an even integer, right? It's 2 times a number, but we really need to know that that k plus 1 is an integer in order to know that n plus 1 equals 2 times an integer. Well, is k plus 1 an integer? Well, sure, because k is an integer, 1 is an integer, and when we add 2 integers, we get an integer, right? That's called closure, a closure property. We're saying the integers are closed under addition. And what closed under addition means is that adding 2 integers always gives you another integer, and that is a property that is true of integers. Anytime you have 2 integers and add them together, that gives you another integer. So k plus 1 is an integer by closure under addition, and it looks like that's going to give us that n plus 1 is an even number, which is what we want. All right, so let's see if we can line this up. Again, so when we write our formal proof, we know how the logic is going to work. So we start off with n being odd. That tells us that n is equal to 2k plus 1, where k is an integer. That tells us that n plus 1 equals 2k plus 2, and that equals 2 times the quantity k plus 1. We need to prove that k plus 1 is an integer, which it is, since the integers are closed under addition and that k and 1 are both integers. Right? And again, closure under addition just means that adding two integers gives you another integer. And then since n plus 1 equals 2 times k plus 1, that means that n plus 1 is equal to 2 times an integer, and so that's going to be an even number. So that's an outline of our proof. Now we're going to write a formal one. And just so you know the rules of writing a formal proof, it's going to be just like our informal proof in terms of our logic, except we have two things that we got to be very careful about when we're explaining things. We need to make sure when we're explaining things, we're carefully explaining the logic of what we're using. We want our proof to be logically sound. We want to make it sure that peeves cannot criticize it. We want to shut peeves up as much as possible. And the second thing is we need to be nice to our reader, right? We need to remember that this proof is for other people to read. We want to make sure our reader is not going to be unhappy with us when they're reading it. First of all, they need to be happy because the proof is logically sound, but also we need to make sure about things like make sure the reader understands what we're assuming, make sure that the reader understands all our logical deductions, make sure our reader knows where they are in the proof so that, for instance, when they get to the end of the proof, they're not just left hanging thinking, is this the end? Is there something more? Was this what they were supposed to prove? We need to help them along. All right, so here's our theorem. If n is an odd integer, then n plus 1 is an even integer. So our first thing is we're going to let our reader know what we're assuming. We're assuming that n is an odd integer, and we're going to let our reader know what we're showing. We're going to prove that n plus 1 is an even integer. So that way, when we get to the end of the proof, we can say, hey, look, that's what we were trying to prove. All right, since n is odd, we're assuming it, right? We can write n equals 2k plus 1, where k is an integer. We're letting our reader know where we are in the proof. We're at the beginning. By adding 1 to both sides of that equation, we get n plus 1 equals 2k plus 2. Again, letting our reader know what the steps we're taking in our proof and letting them know that the logic is correct. By the distributive property, we have 2k plus 2 equals 2 times the quantity k plus 1. That's us just factoring out the 2 from that expression. And so n plus 1 is equal to 2 times the quantity k plus 1. Now remember, the next step we use our closure to prove that k plus 1 is an integer. Recall that k is an integer. Since the integers are closed under addition, we have that k plus 1 is also an integer. And that gives us that n plus 1 equals 2 times the quantity k plus 1, and so it follows that n plus 1 is twice an integer, which means that n plus 1 is even, and that completes the proof. All right, so proofs are going to be something that is, of course, important in this class, but is also important to you as computer science people, right? And I want to explain a few things that are really important. First of all, when you're writing a code, you need to make sure that your programs have a tight logical structure, right? So that they make sure and work the way that they're intended. You need to be able not just to sort of like test the program and say, well, it seems like it's working okay. You need to be able to read your program, read your code, determine with certainty, logical certainty, whether or not it's going to do exactly what you want it to do, right? And what is that but an informal proof? And the last thing is that the writing skills that you use in writing proofs are important as well. There is nothing more frustrating than reading a bunch of code that is poorly documented, so you have to go through line by line figuring out what this darn thing is doing, right? Being able to write good documentation is the sign of a good programmer. All right, so now I think you're ready to work on some proofs of your own. The PDF file is called Introduction to Proofs, and it's included with this video.